we're going to do in 19.2 is we're going to balance half reactions, oxidation and reduction half reactions. And why we're going to balance half reactions is we're looking at the number of electrons that are being transferred in that reaction. Remember, oxidation reduction is a transfer of electrons. Now we want to balance what that transfer is. Say if we look at this list of assigning oxidation numbers down here, it says, and these are the rules we talked about last time, that all elements in their free state are 0. So if we have sodium metal, it again has an oxidation state of 0. Chlorine as chlorine gas has an oxidation state of 0. The next thing we're going to look at is oxygen, which is O's minus 2. Again, unless it's in peroxides, we're not going to see that a lot. The classic example is hydrogen peroxide, H2O2, in which case it is a minus 1. Hydrogen, we can trust to be plus 1 most often, unless it's bonded to a metal hydride. Not going to happen a lot, but we could have a lithium hydride here or there. We'll be able to pick out when it's a negative 1, because normally they put it in the second position when it is a negative 1. Not something we need to worry about, because it's not going to happen very often. The sum of those oxidation numbers has to be neutral for a neutral compound, so it has to add up to 0. So with sodium chloride, we have chlorine together. Well, chlorine's always a minus 1, it's a halogen. Sodium is a plus 1. Again, overall, it equals 0. Now, notice there's one more rule that says that oxidation state for an ion has to be equal to the charge stated. So if we have a nitrate, NO3 minus 1, we can still use the rule that says oxygen is minus 2. There's 3 of them, that's an overall negative 6. If we have an overall negative 1, well, nitrogen has to be plus 5. So hopefully we remember that from the last podcast. The other thing we want to do is identify what is being oxidized and reduced, and use the correct terminology. So there is some slightly additional terminology we need to add. So we'll use that example, sodium and chlorine making sodium chloride. And I'll balance this correctly. So we already identified these being 0 and 0, this being plus 1 and minus 1. So sodium is getting more positive. If it gets more positive, the way it got more positive is via this. It was oxidized. It got more positive. It lost electrons. Notice the electrons in that equation are on the product side. The products are the electrons. It lost some electrons. It was being oxidized. So this was oxidized. It went through oxidation. The funny thing is it's called the reductant, or the reducing agent. Whatever's being oxidized is the reducing agent, because it reduced the other thing. That's what gets a little bit tricky about this. The oxidant, or the oxidizing agent, is the thing being reduced. So notice chlorine went from 0 to a negative 1. It gained electrons, so it was reduced. So a little bit tricky with terminology. The thing being reduced is the oxidizing agent. The thing being oxidized is thus the reducing agent. But hopefully as we use these more, they'll make more sense. Now, let's do something here. I want to split this reaction apart into the oxidation, into what we're going to call half reactions. So our half reactions we can write as the oxidation half. We have sodium, and what's sodium doing? Sodium is going to a plus 1 on the other side. So that's my oxidation half. Now I'm going to write my reduction half. So chlorine is reduced. It's going to a negative 1, and that's my reduction half. Okay, so I have my two reactions. If we're balancing these half reactions, what we need to have in here is the electrons. So just like this states, we need to put the electrons on the right side. So I'm going to go in and say, well, notice sodium lost electrons, so I need to put 1 electron over here. Notice overall this half reaction is balanced. This overall is neutral on this side. Overall on this side, it is also neutral. So if we're oxidizing, we're losing electrons. Notice oxidation, losing electrons, electrons go over here. So the sodium lost an electron. So we should be able to write each half reaction kind of as its own unique reaction. For the second one, what I have to do first is I have to balance that element. Notice I can't have 2 chlorines and then just 1 over here. So I need to balance that first, but now I can add in my electrons. Again, chlorine gains some electrons. Each one gains 1, but now since I have 2 of them, I have to say 2 electrons. So this is now my balanced half reaction. Again, notice that overall my charge is balanced as well. So notice I have 2 negative 1 ions. That's an overall negative 2. And on the other side, I have a negative 2 electrons, which has negative 2. So it's negative 2 on both sides. It doesn't have to be neutral on both sides, but the two sides have to be equal. Now what we're doing, if we write half reaction for oxidation or reduction half, The next thing we're going to want to do is put these back together. We want to balance this as a half reaction method. So what I have to do when I balance them is I have to balance them based on the electron transfer. Notice chlorine needs to gain 2 electrons, sodium only loses 1, so what I have to do is multiply this whole reaction by 2. And so what I'll have, and maybe I'll just write it underneath, is I'll have now 2 sodiums reacting to lose 2 electrons and making 2 sodium ions. So now what I have is I have my 2 half reactions, and I've balanced the number of electrons, and I could add these reactions back together. So this is what I've done. We had this reaction. That was a redox reaction because we had electron transfer. We had identified the oxidation half reaction. The oxidation half reaction, by the way, again, is losing electrons. We had the reduction half. Then we balanced them, put them back together. Now notice one thing we might want to do is there is a moniker to help us remember this process. It's called oil rig. Oil rig, where oxidation is the loss of electrons and reduction, I'm just going to put red, is the gain of electrons. So if you're having a hard time keeping those straight, oxidation is losing electrons, reduction is gaining electrons, and it is the oxidizing agent that is reduced and the reducing agent that gets oxidized, just like it says here. Okay, let's look at some more complicated ones than sodium chloride. That's pretty easy. Okay, so I'm going to do this first reaction here. And notice I have a bunch of rules for balancing these half reactions. Now, most of them we don't need for this reaction, but we're going to do the first one. So step 1, we want to divide the equation into 2 half reactions. So I have chlorine going to chloride, and notice that gets more negative. It gains electrons, so reduction is gain. This is my reduction half. So I also want to identify what's my oxidation half and reduction half. On the other side, we have iron, metal. And notice they're just giving us the ions right now. They're making it easy on us. And just let them. Don't be worried about it. Just take the ions. If they're going to give you the ions, take them. So that's my oxidation half. So I've divided my equation into 2 half reactions and identified them. Now it says balance the atoms other than hydrogen and oxygen. So I have to balance. Notice I have 1 iron here, 1 here. I don't have to do anything there. But 2 chlorines, I need to put a 2 here. Okay, so I've done step 1. I've done step 2. It says balance oxygen by adding water. I don't have to do that right now. Hydrogen by adding hydrogen. I don't have to do step 3 and 4. Those sound kind of goofy. I'm going to wait on those. But now it says balance the net charge by adding electrons. I can do that. Notice I have 2 chlorines over here, so I need to add 2 electrons to the other side because that's my reduction half reaction. It gained 2 electrons. On the other one, now what happened to iron? Iron lost an electron. So I'm going to put 1 electron over here. Now notice the overall charges on each side balance. Overall, that's a +2, and this is +2. Now, notice it says make the electron gain and the electron loss equal, and then add our half reaction. So we can do that. So notice iron lost 1, but chlorine needs to gain 2. So I'm going to take this whole reaction here and multiply it by 2. Okay. So now I have 2 electrons plus chlorine. Notice I didn't have to multiply this by anyone. And I'm going to write my other half reaction. Now I have 2 irons yielding 2 iron plus 3s and 2 electrons. Now what we can do is we can put these half reactions back together. Notice there's 2 electrons here and 2 electrons on this side, so they cancel. Put the reactions together. I have 2 Fe, 2 plus chlorine, 2 Fe, 3 plus 2 chlorides. Okay, that's oxidation reduction reaction balanced by this half reaction method. That is it. Now again, that was a little bit easier. We can get more complex. So now we have one that's more complex. Notice we have our permanganate ion with bromide making permanganate ion itself, or manganese ion itself, and bromide. So first thing we want to do is this gives us a lot of ions, but I'm not really sure what's being oxidized and reduced yet. So I'm going to rewrite this and try to identify what's going on. So they just give us the ions and the neutral elements. So easy stuff first. Bromine by itself is 0. Over here bromine's negative. So bromine just got more positive. So bromine was oxidized. So I have actually my oxidation half reaction. Be Br going to Br2. That is my oxidation half. I have that done. Okay, Let's find what's being reduced. Let's see. Weird thing, there's only oxygen here. Goofy. But I know oxygen is -2. There's 4 of them. That'd be a -8. So if there's an overall negative charge, that means manganese plus here must be a +7, which is kind of silly, but it's charged, so it's not silly, it's just its charge. So manganese goes from +7 to a +2. That means it gained a ton of electrons and it was reduced. So my reduction half reaction is, I'm going to take that whole manganate ion, I don't take anything off of it right now, going to manganese +2, that's my reduction half. So I have divided the equation into 2 half reactions. Okay, identified. Actually, what we should have to do before that is identify what's being oxidized and reduced, and then we can divide it. Now it says balance all the atoms that aren't hydrogen or oxygen. Okay, so in this one we have 2 bromines, so I need to put a 2. In this, 1 manganese, 1 manganese. Notice it says anything that's not hydrogen or oxygen, everything else is hydrogen or oxygen. Now notice in step 3, this is where it's kind of silly. It says balance the oxygen by adding water. So if we have any polyatomic ions that have oxygens in them, we can balance that. We'll do it by adding water. So I'm going to add water over here. And how many do I need to add? I need to add 4. So let me give myself a little bit more room. I'm going to add 4 waters. And you're going to say, why 4 waters? Well, it's because there's a 4 by the oxygen here. So that's how I get 4 oxygens to balance. So my oxygens are balanced. Now, after we balance the oxygen, then notice in step 4, we balance the hydrogen by adding hydrogen ions. So we have to add those to the opposite side. Now, why we can do this is because most of these reactions will happen under acidic conditions. Occasionally, they're under basic conditions. We'll talk about those examples later, but most of them, we're going to have acidic conditions. So I'm going to add 8 hydrogen ions here. So 4 times 2 is 8. I need 8 hydrogen ions. Okay, starting to look a little bit goofy, but stay with me, please. Don't start crying. Step 5. Now we need to balance the net charge by adding the electrons. So we have to add the electrons to the right side. So bromine is a -2. It was oxidized. It lost electrons. Each one, it lost 1 each. So 2 electrons go over here. Now manganese, again, remember, it went from a +7 to a +2. So it gained 5 electrons. So I have to put 5 electrons over on this side. Let me make myself some room. Okay, so I can fit in my 5 electrons. So, and one thing I'm going to check to make sure it's right is I'm going to make sure the charge on this side equals the charge on this side of my half reaction. This side's easy. Overall, it's a +2. This side we have -5, -1, that's -6, and a +8. So that is a +2 as well. Okay, so they balance. Now, if we go back to our rules, we need to make the gain and the loss of electrons equal, and then add our half reactions. So we have 5, we have 2. Ooh, I could multiply it by 2.5, but I bet I'm going to have to use whole numbers. So I'm going to multiply this whole bit by 5, and everything here by 2. That'll be my lowest common denominator. Let's see what we get. Okay, so notice I multiplied everything in the top by 5, everything in the bottom by 2. Everything, every piece. Now notice, good thing that I see coming out is there's 10 electrons here and 10 electrons here. That makes that easy. We know they cancel. And now we're going to add everything on the left side of the arrow. On the left side, keep everything on the right side of the arrow on the right side, and put these 2 reactions together. So 10 bromide ions plus 2 permanganate ions plus 16 hydrogen ions. And that should yield 5 bromides and 2 permanganate ions and 8 waters. So in our final balance equation, we need to have the water and we need to have those hydrogen ions. We absolutely do. Again, if there was any oxygens and we had to use that process. Let's go one step harder. Okay, so here's one from your book. So the first thing, it says balance the oxidation half reduction reaction. And we want to do it by the half reaction method. So the first thing we have to do is identify what's being oxidized, what's being reduced. Right away, what stands out at me is bismuth is by itself at 0. I'm going to take care of the easy stuff first. Over here, it is attached to a hydroxide ion. And there's a 3 outside that hydroxide. Just from knowing my polyatomic ions, I know hydroxide is always -1. So bismuth must be the +3 here. So bismuth is going from a +3 to a 0. So in that way, it's really helpful to know what your polyatomic ions are, because you know what that overall charge is. Now I could go and take apart the oxygen and the hydrogen in there. I'm not going to do that yet, because I think that oxygen's -2, that hydrogen's +1, and that's how it gets that overall -1 charge. So I'm not going to worry about that yet. Sodium, again, in alkali metals, I was +1. Over here, sodium's in the first position, again, +1. Notice there's 2 of them, so that gives an overall +2 for that compound. Oxygen's in that compound too, it's -2. There's 2 of them, that's a -4. So let's see, I know the sodiums are saying +2, the oxygens are saying -4. It's a neutral compound, so tin must make up the difference, it must be a +2. So tin is a +2, I'm going to investigate tin over here. Notice my number of oxygens changed, now I have 3. 3 each -2, that's an overall -6. I have 2 sodium, so that's +2 overall. So tin in this case, again, is a neutral compound, tin must be +4. So tin went from a +2 to a +4. So that was oxidized. So we have bismuth and tin. Now, I'm not going to worry about the water. I'm just not going to worry about it. So now what we can do is we can write the half reactions. And the thing it allows you to do is we can, one thing it suggests is to write everything as a net ionic equation. What I'm going to do is eliminate any ions that are kind of spectator ions that aren't changing in this. So sodium is +1 on both sides. I'm going to get rid of that. And I'm going to get rid of my hydroxide and my water. I'm going to leave those out. So I have a bismuth. I'm going to get rid of the things that aren't changing, essentially. So I have bismuth going to bismuth solid as 0. Okay, that is getting more negative. It's gaining electrons. So that is my reduction half reaction. Now I'm going to write my oxidation half. Now notice I can remove those sodiums. If I remove 2 sodiums, I have SnO2 with a -2, and it's going to SnO3 as a -2 ion. So notice I can leave off those ions because those aren't involved in the reaction. This is the part that people kind of it's the hardest part when you start this, is removing the ions that aren't part of the reaction. It makes it easier to balance if we do this. So that's our first step. That's the oxidation half. Now it says we have to balance the number of elements. Bismuth, there's 1 bismuth, 1 bismuth, 1 tin, 1 tin. I do have to balance the oxygens. There's 3 here, there's 2 there. I'll need to add 1 water to the left side of this reaction. So plus water. If I add 1 water, that means I need to add some hydrogens to the other side. Plus 2 hydrogens. Okay. Now, let's see. Elements are balanced. Oxygens, hydrogens balanced. Now I'm going to balance my electrons. So bismuth goes +3 to 0. So it is reduced. So I was about to put the electrons on the wrong side. The electrons go over here. Right? Because then notice my overall charge is equal. You can always check if you put the electrons on the right side, because people have that problem too, by making sure that the overall charge is neutral. Or at least equal on both sides, I should say. That side is fine. Okay, down here, let's see, tin again went from a +2 to a +4, so that means it lost 2 electrons. So it lost 2, they should go over here. Now our overall charges should be equal. We have overall a -2 charge here. We have overall a negative, let's see, -2, -4, +2 is a -2. So it's -2 overall on that side as well. Now we're going to balance the right number of electrons. So 3 and 2, there's 3 here, there's 2 electrons here, so this needs to be multiplied by 2. This whole bit, we're going to multiply by 3. So hold with me. This is really where your handwriting comes into effect. It's good to have good handwriting skills so people can read what you're writing. Sorry, that was a little bit messy. So 6 electrons plus my SnO3 minus 2. Okay, now good thing. I have the same number of electrons on both sides, so I'm going to cancel those with my 6 electrons over here. I'm going to keep everything on the left side of the arrow, on the left side. So we have bismuth, and it doesn't matter the order you write it in, as long as it's on the correct side of the arrow, or the reaction symbol. Plus water yields 2 Bi plus SnO3 minus 2 plus 2 hydrogen ions. Okay, so now we have it. We've put it back together. This is actually our balanced net ionic reaction. So if someone needed to know the balanced net ionic reaction, we now have it. Now sometimes what they'll want you to do is add ions back to both sides. Oops, I forgot my 3. There should be a 3 right here. And I didn't multiply my hydrogens by the right number. That should be 6 hydrogens. Thank you for catching that, virtual student in virtual land. I was wondering why this wasn't coming out right. That makes more sense. 6 hydrogens there. Okay. So when I have it finished written, this is what it's going to look like. Now sometimes they're going to ask you to add the ions back in at the end. Most often not. This is the answer they want. This is our net ionic reaction that's been balanced by the half reaction method. Now I'm going to make, this one's getting a little bit long, I'm going to put some more examples out there in a part 2, kind of a sequel. So if this gets really popular, hopefully the second podcast will be popular as well. Normally there's a drop-off in popularity for sequels. They're never as good as the first one, but this is our half reaction method, balancing some equations by it, and writing the net ionic reactions based upon the half reaction balancing. And there'll be more to come.